Before we start analyzing a three-step parallel plate capacitor, we shall understand how capacitance is calculated for a simple configuration of parallel plates. Let us have two parallel conducting plates. There will be positive Q charges on one plate and negative Q charges on the other plate, such that the charge density on one plate equals plus Q by A and on the other plate it is minus Q by A. A is the area of each parallel plate and D is the distance between them. Because the plates are conducting, the charges get uniformly distributed, and because of that the electric field inside the plates is uniform and it is normal to the surface inside. The electric field inside the plates E equals rho divided by 2 epsilon naught. Its direction is from positive plate towards negative plate. Total electric field inside the plates equals electric field due to positively charged plate plus electric field due to negatively charged plate. Therefore, E equals EA plus EB. Magnitude of electric field equals rho divided by epsilon naught, which is equal to Q divided by A epsilon naught, where rho equals Q by A. The potential difference V between two plates equals electric field multiplied by distance D. V equals ED equals Q times D by A epsilon naught. Therefore, capacitance C equals Q by V equal to A times epsilon naught divided by D. This is the formula for capacitance for the parallel plate capacitor. If a dielectric constant K is introduced between the two plates, then the capacitance of the arrangement will increase K times. We shall get back to the original question now. The question is, a capacitor is made up of flat plate of area A and a second plate having a star-like structure as shown in the figure. If the area of each star is A by 3 and the height is D, what is the value of the capacitance of the arrangement? As in the diagram, plate A is horizontal but plate B is in the form of steps. Area of each step is A by 3 and the distance of each step increases by D. Total capacitance equals sum of the capacitance due to each step, which is equal to C1 plus C2 plus C3. Capacitance due to first step equals area of first step multiplied by epsilon naught divided by distance of first step, which is equal to A by 3 multiplied by epsilon naught by D. Capacitance due to second step equals area of second step multiplied by epsilon naught divided by distance of second step, which is equal to A by 3 multiplied by epsilon naught divided by 2D. Similarly, capacitance due to third step equals A by 3 multiplied by epsilon naught divided by 3D. Add all the three capacitance values. C equals A epsilon naught divided by D multiplied by 1 by 3 plus 1 by 6 plus 1 by 9. On simplification, you will get total capacitance equals 11 by 18 multiplied by A epsilon naught by D. And this is the answer. We shall look into some more interesting exercises of different types. A parallel plate capacitor of capacitance 12.5 picofarad is charged fully by a battery of 12 volt. After disconnecting from the battery, a dielectric slab of epsilon R equal to 6 is inserted between the plates. What is the change in potential energy after inserting the slab? In this example, the only thing that is conserved between both the cases is total charge Q. After inserting a dielectric between the plates, the capacitance value changes, so the voltage across the plates also changes. Let us calculate the total electrical energy stored in the capacitor when it is fully charged by a 12 volt battery equal to E1, which is equal to half CV square, equal to half into 25 by 2 multiplied by 144, which is equal to 910 to the power minus 12 joules. Total charge Q before and after inserting the slab remains same. Because Q is same, C1 V1 equals C2 V2. Therefore, new voltage across capacitor after inserting the slab equals 12 by 6 volt. Electrical energy stored in the capacitor in the second case equals 150 multiplied by 10 to the power minus 12 joules. Therefore, change in potential energy equals 750 10 to the power minus 12 joules. In the circuit given below, the energy stored in the capacitor is N microjoules. What is the value of N? To calculate the energy stored in the capacitor, you need to find potential difference across the capacitor and use the formula energy stored equals half CV square. Electric current I1 in the first branch equals 1 ampere. Electric current I2 in the second branch equals 2 amperes. VA minus VC equals 3 times I1 equals 3 volt. VA minus VD equals 4 times I2 equals 8 volts. Subtracting one equation from the other, voltage across the capacitor equals VC minus VD equals 5 volts. Therefore, electrical energy stored in the capacitor equals half CV square equals half into 6 into 5 square equals 75 microjoules. Therefore, N in the question is equal to 75. Two parallel plate capacitors having equal plate area of 200 cm square are joined in such a way that A is not equal to B. If the equivalent capacitance of the combination is X epsilon naught farads, what is the value of X? Given that plate area of 200 cm square, capacitance C of the combination is epsilon naught A divided by D minus C. Plugging in the given values, you will get X equal to 5. With this exercise, we are ending this video. Thank you for watching.